This is physics in the AM. It's the vectors coming at you live. We've talked about Newton's three laws, and we're now putting them together to solve some problems and stuff like that. Okay? And as far as these laws, we said the first law is the one where object in motion stays in motion unless acted upon by an external unbalanced force, or it stays still, motionless, unless acted upon by an outside force, unbalanced. Second law, sum of forces is mass times acceleration. Third law is the equal and opposite kind of idea, action-reaction forces. Then we looked at being inside an elevator accelerating positively or negatively with your motion, how that affects your weight. And on the opposite side of your handle, take a look at this. We'll read through it here. Forces of ropes and strings. Okay. Have you ever noticed, maybe you have or haven't, if you have something on a rope or on a string, it's likely, and it's just hanging there. Now I'm pointing up at these as if these are weak strings here, and I'm pointing up at those plugins. If there was a heavier mass on it, it's pretty safe right now, but when is it likely to break? When you like jerk it up, if you were to like on the third floor and you somehow pull it up fast, you know that for a moment there, that tension on the string increases when you pull hard on it, right? There's a chance it could break. So let's read this, and you got it in front of you. Tension is simply a specific name for the force exerted by a string or a rope. Simplification within this textbook is the assumption that all strings and ropes are massless. That just makes our problems easier. Okay? We won't take into account the weight or the mass of the rope. To understand tension in more detail, consider this situation over here in this. I've got a bucket hanging from a rope attached to the ceiling. The rope is about to break in the middle. If the rope breaks, the bucket will fall. Thus, before it breaks, there must be forces holding the rope together. The force that's at the top of the rope exerts on the bottom part, F, top and bottom. So you see this here? T, tension, force, top on bottom, pushing up. Newton's third law states that this force must be part of an interaction pair. The other member of this pair is the force that the bottom exerts on the top, bottom on top. Oh, right here. Hey, look at that. They're equal and opposite. Okay? Think about this situation in another way. Before the rope breaks, the bucket is in equilibrium, equal forces up and down. This means that the force of its weight, just a second here, I'm trying. The force of its weight downward must be equal in magnitude in the opposite direction, the tension in the rope up. Okay? Similarly, if you took a point in the rope just above the bucket, it's also in equilibrium. Therefore, the tension of the rope below it, pulling down, must be equal to the tension of the rope above it, pulling up. You can move up the rope, considering any point on the rope, and see that the tension force up and down is equal. At the very bottom, the rope has a tension equal to the weight of the bucket. The tension everywhere in the rope is equal to the weight of the bucket. Thus, the tension in the rope is the weight of all objects below it. Does that make sense to this? Now, because we're saying it's a massless rope, it gets confusing if you start talking about the mass of the rope, but it's negligible compared to assuming a heavy bucket. Okay. Next paragraph. Tension forces are also at work in a tug of war, like the one shown in, I don't think I have it on this page. Okay. If team A, but you can imagine a tug of war. Team A on the left is exerting 500 newtons in the rope. It doesn't move. When team B on the right also must be pulling 500 newtons. So what's the tension of the rope in this case? Think about it. I'm pulling 500, you're pulling 500. Is it 1,000 newtons? To decide, think of the rope divided into two halves. The left-hand side is not moving, so the net force on it is 0. Force applied on the rope is equal to force right on left. The right-hand side, I guess this way for you guys, pulling on the left. 500 newtons. Similarly, the opposite scenario, left on the right, 500 newtons. The two tensions, left and the right, are in interaction pair, so they're equal and opposite. Thus, the tension on the rope equals the force with which each team pulls, or 500 newtons. To verify this, you can cut the rope in half and tie a spring scale like this. This is the tug of war, right? It doesn't matter, right? Like, you guys follow what I'm saying? Okay. So it's not doubling it up. My point is, would this make any difference if my tug of war was I attach this to the wall on a hook and I pull like this? Would that make any difference whether it was me and Sheldon pulling and we each pulled with 100 newtons? I guess 8, if that's it. 8 newtons of force. Or if I just said, nope, Sheldon, I'm going to just attach to the wall, and I pulled with that same 8 newtons of force. Does it make any difference as far as the rope is concerned? You follow me? This can get confusing. So, I think at the bottom of yours, did I put a question at the bottom? Yeah. We're going to work through that question in a second here, and just a second. But before I do, I'm going to pause here because it's a demonstration. Forces. Consider this. Let's start thinking about some things that are kind of counterintuitive. That's why I showed you that demonstration. Pretty simple. Simple to do. Not simple to think about, though, is it? So, lifting a bucket. You're lifted by a rope. The rope will not break if the tension is 525 newtons or less. So, meaning that if you really jerked it fast, gave it an acceleration, because we know acceleration can create force, right? It would break. Is the rope in danger of breaking under those conditions? Moving at 3 meters per second. Okay. Well, we need a free body diagram, even if it's not explicitly stated you need it. So I'm going to put my box, I tend to use a box, 50 kilograms. There we go. Just giving myself a little more space. Now, we've got a tension, it's a rope. I'll call it T for tension. And we know the tension force can't exceed 520. Not that it's that big a deal, it's physics class, but did you know that the word cannot is one word? Don't look stupid and don't call it two separate can space not, right? Cannot is one word. I don't know why. Do not is not one word, but it is. Can't. Let's see, 525 meters. Now, what is the other force on here that we have? Why is there tension on there? Because there's a weight force, right? Fg. We can calculate that. If it's not moving, they're equal and opposite. And it's negative mg, right? I'll call it m with negative g like this. We consider g to be 9.8 without a sign. And then I just toss in the negative sign as needed, depending on how you draw your diagram. And in this case, it's a 50 kilogram force, or 50 kilogram object. negative. I'm going to use 9.80. Pretty significant. I haven't calculated it out. It's 490. Downward. Okay. Now we're understanding in the context of this problem, negative means down, positive means up. Now, a few things here. Let's list what we have. Well, if the acceleration is constant, I need to know what the acceleration is, though. See if it's in danger of breaking. The bucket started at rest, so V1 is 0. After being lifted 3 meters, and it's positive, so say 3.0 meters, positive direction. Speed, 3 seconds. So the idea is, I'll just draw into a box here for a second. Is this slow enough that I picked up speed slowly enough that I don't put too much tension on the rope? Because if I go fast, it may jerk too much and apply too much force. This is related to that elevator idea, right? It always has gravity working down on it, but we know that it's adding into the acceleration, sort of like the weight force artificially, I guess we could say, increased if you really jerk it up fast. Is that too much for the rope to handle? Will it exceed a tension of 525? Right now, at rest, it's 490 newtons up, right? That's understood. Okay. The minute we get 525 up, though, we have to keep listening. We have a problem. So we've got 4 variables, we need the equation. We have 3 variables, and we want a 4th. That equation is, now you'd always have access to your equation sheet, but the v squared one. So I'm going to put it right here. V2 squared is equal to V1 squared plus 2AD. Hey, I made my A the other way around. I hardly ever do that. Anyway, so I'm going to toss in my numbers. So I got my 3 meters per second. Squaring it. 0, so I don't even have to square it. 2, I'm wondering what A is. 3 meters. This is simple enough that I can do the arithmetic without a calculator. I got 9 on the left. Two times 3 is 6. Then I divide my 9 divided by 6, and I get 1.5. Okay. I now have acceleration of the object. Now, yesterday we simplified that whole elevator example to whether or not you just add or subtract with gravity, the 9.8 meters per second squared. You could add the 1.5 to it, and then just see what the tension will be. But I'm going to do it from first principles again, okay? I'm going to just change colors here to Newton's second law. And we're going to say in the y-axis on our diagram, always state that. Some of the forces, and that's pretty crappy sum. Epsilon, some of the forces, mass times acceleration. Toss in, that's a positive upward acceleration. So the sum of the forces, we've got Ft and Fg. We got M. Ft, that's what we're looking for. Will it be 525 or bigger? I'm going to drop the arrows, stuff we understand. Fg is negative, and what was it down here? 490. The mass was the, was it 50? Yeah, 50 kilograms. And 1.5. Okay. Now it's an arithmetic thing. 1.5 times 50 is 75. Ft, I'm going to add the 490 on to the other side. Equal to 75 newtons plus 490. That's going to be a positive 560. So the rope breaks, right? Is it 525? No. The rope breaks. We could have done it the other way that we did with the elevators. Once you know that the acceleration due to gravity, add it on. So we're 9.8 plus 1.5, and then just calculate it with the 50. You come up with the same thing. Okay? Now, we'll get you some additional problems here later, but I'm thinking right now, I took a break to do that relativity introduction. We needed a break, so we'll continue on with this break here. I'm going to pause the thing. But I'll show you the questions just so it's on the video here. It's in your textbook on page 106. Not that you need to turn to them right now, but 32 and 33. If you're at home, I know who's at home.